Good day, everyone. My name remains Salah Ismail, the chemistry tutor. You're welcome to another edition of our Chemistry Made Easy tutorial classes. So today is going to be the third series of transition metal classes. We've had the very first series on transition metal. We're also taking the second series of transition metal. So today, we shall be discussing the third aspect or the third series of our classes on transition metal. So today, our class is going to be centered on ions, most importantly, the extraction of ions. So keep relaxed and enjoy today's series. Now, we know iron is actually one of the very foremost transition metals, as we've seen in our previous series, and we quite much understand the fact that iron is very, very important in our daily experiences. One of the very prominently only used elements in our every day-to-day activities. So that's why it's quite important and prominent for us to discuss metal, being one of the very important aspects of our scheme too. Now, iron is the second most important abundant element or the abundant metal found in the earth crust. So this is quite important to note. Iron happens to be the second most abundant metals in the earth crust. It's not found in a free metallic state. It's always found combined with other elements. So except you find it in the meteorites. So the meteorites are mostly composed of ions only. But apart from that, we can find iron in the earth crust mixed up with several other constituents or components. As a result, iron can exist in some major forms of ores. So we can always see iron existing in forms of their ores like hematites. So the hematite is actually Fe2O3, that's the iron 3 oxide. We also have the triiron tetraoxide, that's the Fe3O4, that's called the magnetite. Okay, that's the second most prominent ore of iron. So after the hematite, then we also have the iron 2 triisocarbonate 4, which is called the spathic iron ore. So iron 2 triisocarbonate 4, that's the Fe, right, CO3. So that's also another common ore. Then you have the limonite, right, which is a hydrated form of the hematite. And then you have the iron pyrites, same as iron sulfide. Then we have the siderites. These are the common oxides of metal iron. Common ores of iron that are commonly found are the hematite and the magnetite. So that should be very, very taking note of. Then iron is also present as triazosilicate 4 in clay soil. So it is a constituent of the pigments in hematite in animals and chlorophyll. So the major components present in the pigments of the hemoglobin, we definitely know that the function of the hemoglobin is to capture oxygen and then get it circulated throughout the body part, which is needed for the cell for cellular respiration. And apart from the fact that the iron is present in the hemoglobin of animals, they also have iron in the hem of the chlorophyll in the plant. These are very prominent components which have iron present in them. Our focus for today is actually to discuss the extraction of iron. So how is iron being extracted from the earth? So iron is extracted industrially by a process called reduction of the oxide. So we can extract iron through a process of what? Reduction. So you have reduction of the oxide using a blast furnace. The blast furnace is actually the material or the engine, the equipment that is used to have the extraction of iron done in large scale. So the ore usually, which is the hematite, that's the prominent ore of iron, right? So the ore, which is a Fe2O3, right? So that's the hematite, is roasted in air so that iron 2 oxide is produced. So that's one of the very first things that is done before the extraction is mainly done in the blast furnace. So the very first thing is there's going to be roasting of the roasting of the hematite, right, in air, which is going to lead to the formation of the iron 3 oxide itself. So we are going to have this component being produced while the iron ore is heated in air. Now, the iron 3 oxide is then mixed up with the limestone and coke at a very high temperature in the blast furnace. So for extraction to occur, the following materials are actually required. You have the iron 3 oxide, that's the Fe2O3, right? We have mixed up with the limestone, so you also have CaCO3 as part of the constituents. And then you have the coke. Coke is carbon, right? Coke, carbon, and very high temperature. So the temperature is about 2000 degrees Celsius used in melting the substances to obtain the iron of desired quality. Now, the solid materials are fed into the furnace from the top. So we can see here the furnace. So all these solid materials are actually placed into the furnace here from the top. We are going to have the iron ore, the coke, and the limestone all placed from this top, right, of the blast furnace. So we can see here the blast furnace, right, all the the reactants, the materials needed for us to do this extraction are inserted to the top part of the furnace. So thereafter, we can see here that after the solid materials are fed into the blast furnace from the top, where a blast of hot air enriched with oxygen enters near the blast through a series of small air tubes called the tuyeres. So we can see here that hot blast air is going to be made to pass through this path of the blast furnace, which is known as the tuyeres, right? So both portion here are known as the tuyeres. So it's like they are like tubes upon which hot air are being blasted into the furnace. So you can see the temperature of about 1800 degrees Celsius, right? All what you have here are nothing but coke. So you have coke in here, coke in here. So this is what is making up the composition of the blast furnace within here. But do not forget that apart from coke, we have several other entities like the iron ore itself, the coke, the limestone, which are actually required in the process. Now, why the hot air is made to enter through the tuyeres tube down into the lower chambers of the blast furnace, then some chemical decomposition begins to occur. So we can see that here. Now, the very first thing is that in the lower parts, the coke is oxidized by the oxygen in the hot blast to form carbon dioxide. So we definitely know that at the lower parts, right, at the lower part of the furnace, we're going to have here carbon reacting with we are going to have carbon here reacting with the oxygen that is being inserted through the tube, the TRS tube. So we're going to have carbon plus oxygen. So that's going to give us CO2. So we'll be having coke plus oxygen gas to give us the CO2. So the very first reaction that occurs at the lower part of the blast furnace, where we have very high temperature, is that the coke is going to react with the oxygen to give us carbon dioxide. Now, in addition to that, it was made to note that this process is highly exothermic, meaning that it involves quite a high amount of heat. So while the reaction is occurring, about 395 kilojoules of heat is emitted, right? About 395 kilojoules of heat is emitted per mole. So here we have the equation, and here we have the energy liberated during this process. Now, this reaction does not stop here. It continues and it proceeds. So while the first reaction occurs, air is going to transcend up the blast furnace. So as the air is moving up to the blast furnace, at this upper region of the blast furnace, we'll be having the CO2 produced reacting with more of the coke. So then the C carbon dioxide reacting with more of the coke is going to lead to the formation of carbon monoxide. That's the formation of CO. So from CO2, the reaction of more coke, then that gives us the CO, that's carbon 2 oxide. So that's the second reaction process that occurs here as indicated here in the equation. So on moving up the furnace, the oxygen in the air lessens and the carbon dioxide becomes reduced by heating more copper to copper 2 oxide in an endothermic process. This reaction, unlike the very first one we talked about, is actually an endothermic reaction, meaning that heat is actually being absorbed. So you have the CO reacting with the coke to give us CO2. And the energy that has been absorbed during this process is about 175 kilojoules per mole. Now, the reaction does not stop here. It continues as we have a number of other substances different from coke, which is the carbon. Now, the carbon 2 oxide generated then reacts with the iron 2 oxide in the endothermic reaction, reducing it to iron in the upper part of the furnace, which is cool. So as you are moving to the upper part of the furnace, you get to realize that this part is becoming cooler, and so at this region we'll be having a third stage reaction. So here our CO, carbon monoxide, then reacts with the Fe2O3, that's the iron 3 oxide, to lead to the formation of Fe, that's the iron with the CO2, carbon dioxide. So at this stage, the iron is then produced through the reduction reaction using the carbon 2 oxide. So you get to realize here that this is summarizing the equation at this juncture. So our Fe2O3 reacting with CO to give us this, and this equation is balanced. This is also a reaction that is exothermic, as heat is also going to be liberated. About 28 kilojoules of heat is liberated per mole. The molten iron produced sink to the bottom of the furnace. So the iron that has been produced at the topper region, right, of the blast furnace then is going to sink due to its density. So it's going to move down from that region where it is formed here. So our Fe moves down to the bottom of the blast furnace. So when it gets to the bottom of the blast furnace due to its density, right, so then it can be collected through this region. So we have the tap hole for iron, where the iron is going to be collected. So that's how the iron will be collected. However, we have a number of other steps that occurs before this extraction is completed. So one of the very fundamental aspects that also occurs as part of the continuation of the reaction is the function of the limestone. So we mentioned limestone as part of the very prominent ingredient that are actually required for this process. So we are having the limestone, which is the CaCO3, right? The function of the limestone, which is CaCO3, is actually to remove the impurities present in the mixture of the ore. So it's going to react with the limestone. The limestone possibly will react with silica, which is actually sand, SiO3. So it's going to react with the silica to form the slag, which is the collection of the impurities. So this illustration is summarized in this equation. So we're having the limestone, right, is breaking down as a result of heat to form the calcium oxide and the CO2. What react with the silica, which is the sand, to form a slag. The slag here is calcium triosilicate for ore, otherwise known as calcium silicate. Now the silicon 4 oxide, being an acidic oxide, reacts with the basic calcium oxide to form the molten triosilicate form, which is actually the summary of the basic processes that is required in the extraction. So finally, here, as the molten iron has a higher density than the slag, two layers are formed at the base of the furnace, and they can be tapped separately. So we can see them here. So we have the layer where the molten iron is getting collected, and then the layer where the slag is also getting collected. So since the molten iron is denser than the slag, the molten iron will be down and it will be collected towards this part down. And then the other one, the slag, is going to be collected towards this part. So these are the channels where those both are collected, and the iron is also being extracted. So it should be noted that the molten iron is run into mold where it is set as a pig iron. So because you have different types of iron, so the very first form of iron that is obtained during this process of extraction is called the pig iron. It may also be used directly to make steel or further purified to produce cast or hot iron. So we have the pig iron, which happens to be the very first iron of extraction. So then this pig iron can be further processed to form the cast iron, and the cast iron can get, from the cast iron you can get the best quality of iron, which is a hot iron. Summary here, we have what shows the summary of the whole equation of the extraction process. Now the very first thing that occurs during the extraction process, as you can see on the screen, this summarizes the chemistry of the whole extraction in the furnace using iron. So the first thing is the burning of coke. So we can see here coke reacting with oxygen to form the CO2. That's the first step. That's the stage 1, right? So the second stage is the reduction of the CO2 to CO. So our carbon dioxide reacts with coke to form what we call the carbon monoxide, and that's the second stage, stage 2. The third stage is the reduction of the iron 3 oxide to form the iron. So the iron 3 oxide is going to be reacted with CO, that is carbon monoxide or carbon 2 oxide, at a temperature of about 1000 degrees Celsius, and then the iron is extracted while the CO2 is formed. And finally is the formation of the slag. So slag is formed when calcium triisocarbonate 4, that's the CaCO3, is decomposed to form CaO and CO2, and finally the CaO reacts with the with silicon 4 oxide to form the slag, which is calcium triosilicate. This helps in the removal of the impurities. So these are the equations that are actually relevant and very important during the extraction of iron. This marks the end of the brief explanation under the extraction of iron. So again, in the next edition, we shall be explaining more about the types of metal, the types of iron, uses, and so have a nice day. We meet again in the next class. Goodbye.